Let's say we've got an incline, a rough incline with a 10 kilogram box being pulled by 100 newtons. The total length of the ramp is 200 meters. Using trigonometry, 200 sine 37 gives me a height of 120, and my coefficient of kinetic friction is 0.5. If we were to figure out the speed of this box as we approach the top, let's say it continues on some distance and that we just don't care about, figure out the speed right there 200 meters later. We're going to first figure out how much work did we do by dragging this box up this ramp. That amount of work is going to be equal to your total energy in the end. This is a conservation of energy situation. So the work done by the tension in the rope, 100 Newton force times displacement is our work equation. So 100 times 200 gives me 20,000. And that equals, at the end, I've got kinetic energy here, I have gravitational potential energy, and it's a rough incline, so there's some kind of energy dissipated by friction. So we have to account for that by using the work done by non-conservative force, in this case, friction. Moving my gravitational potential energy and my work done by non-conservative force to the other side, I get 20,000 minus gravitational potential minus work done by friction equals my kinetic energy. I left kinetic energy all by itself because we're looking for speed, and we know speed, kinetic energy, there's a relationship there, right? 20,000 minus mgh minus frictional force times displacement. Remember, we're on an incline, so our frictional force is given to us by the equation mu times Fn. And in this case, Fn is going to be mg cosine theta because it's the perpendicular to the ramp. Plugging in numbers, we get these. 4,000 equals 5v squared. Kinetic energy is 1/2 mv squared. Half of m is 5 times v squared. Divide by 5 on each side, take the square root of that, and we get something like 28, 30, something similar to